Hi there, this is a section of my 7.4 notes specifically focused on how to partition a segment on the coordinate plane using similar triangles. This first page is obviously just a review for people talking about slope, and the reason why I want to do that is I want to relate slope with length and then eventually get into the similar triangles and partitioning. Alright, so obviously we've been using slope for a long time. Slope is the rise over the run, and you can just count the boxes visually on a graph if you have one. Our rise here is 2 and our run is 9. So our slope is 2 over 9. Slope is really a reflection of how steep or flat a line or a line segment is. Also, the sign is telling you whether or not you're kind of going uphill when going left to right. So if you're going up left to right, then that would be positive slope. If you're going downhill, that would be a negative slope. Recall that there's another way to find the slope, and that is using 2 points on that segment or on that line. So you want to look at delta y over delta x, delta y because that's our rise dimension, and delta x because that's our x dimension. Delta, remember, stands for change of or the difference of. And so there's a formula here that we could use, which you would just take the difference between 2 points and their y coordinates and the difference between the x coordinates of those 2 points. And in this particular example I'm going to write down here, we could say delta y over delta x equals, and I'm going to use this point B here as my y, well, I'll just maybe label it x2, y2, and I'm going to use point A as x1, y1. Substitute in, we can say 3 minus 1 is our delta y, and since I started with 3, I've got to go back to the 10 now. You just have to be consistent. So then you get your 2 over 9. Don't confuse slope with distance or length of that segment. We've been doing this now all year, but they certainly are related. If you look and imagine the Pythagorean theorem here, you want to find this length of this segment AB. It's also referred to as the distance between points A and B. We can use the distance formula, which is derived directly from the Pythagorean theorem. So you're going to sort of imagine a right triangle around that segment, and the 2 legs of that triangle are actually the rise and the run. So you can see here our rise was 2 and our run was 9. We're going to use that in the Pythagorean theorem to find the distance. So c squared equals 2 squared over 9 squared. C squared equals 4 plus 81. C squared equals 85. And then I'm going to take the square root of both sides to solve for that hypotenuse. So C equals the square root of 85. We can approximate that with a calculator. Approximate it because this is certainly not a perfect square. So it's an irrational number, and we'd have to agree with each other as to where to round that decimal, because irrational numbers will go on and on and on, and they will not have a repeating pattern. So we would have to come up with an agreement on where we would round it. Real quick, just a quick review, 85, can we simplify it? Simplified radical. 85 is the same thing as 5 times 17. Both 5 and 17 are prime numbers, so you can't simplify that at all. But we can certainly approximate it. And that is approximately, so I'm going to, whoops, I don't like that color there. It's approximately 9, and I think I'm going to go out to the thousands. 200, yeah, I'm going to go to the hundredths. So I'm going to say 22 hundredths. All right, great. Now, that's just a little preamble here, a review for you, leading into what we're currently focused on, and that is similar triangles. So we're going to use similarity here to partition a line segment. on the coordinate plane. And I'm specifically giving you a ratio that I want you to use. The ratio I want you to use is 3 to 2. And I should have said this. I'm going to say, left to right. I really should have said, what is the 3 and what is the 2. I'm going to say I want you to start from the left and partition this segment AB 3 to 2 ratio. Well, we certainly know from studying similar triangles that, and I'm going to erase this in a second, if I find some value, right now I'm just going to, I'm going to erase this in a second, but if I have some segment here that's parallel to this one, and by the way, I think I'm going to name this vertex C. If I can find some segment here and it's parallel to BC, well then I know that I'm going to create some proportionality. This triangle here, the small one, is going to be similar to the large one, and consequently, because of the triangle proportionality theorem that we have been studying, these segments to each other, these parts, for instance, this segment here is certainly not part of a triangle, but we've learned that these parts are proportional. So the key here is to take this segment here, AC, and partition that 3 to 2. And if we do, then we'll know that these will also be 3 to 2. So that's really the procedure that we are going to work on here. Okay, so we just need to find where this segment is going to be located. So that's our task. All right, so if we have this segment here, we've got AB. Whoops, I lost my vertex C here. We've got this segment AC, and our goal is to partition AC 3 to 2. And we know that AC is 9. I'm just using some space over here. We know it's 9 units long. We want a 3 to 2 ratio, so I can put 3x here and 2x here. So using the segment addition postulate, I've got 3x plus 2x equals 9, 5x equals 9, and x equals 9/5 or 1 4/5, which I can write as a decimal as 1 8/10. If I substitute that 1 8/10 back in here and I multiply that by 3x, I'm going to get 5 4/10 and 3 6/10. And 5 4/10 plus 3 6/10 certainly does sum to 9. So my goal here is to basically make a segment here of 5 4/10 long and then 3 6/10 long. So if I have point or vertex A at 1 1 and I want to walk over to the right 5 4/10, then I'm going to land at 6 4/10. So I'm going to just kind of estimate that or approximate that here on my graph. So right about there is where I want my parallel line. I'm marking that parallel here. It must be parallel in order to create proportionality. By the way, those triangles, as you know, are similar by angle, angle, angle when we do so. All right, so right here, if we look at our segments, I've got a segment here that's 5 4/10 long, and I've got a segment here that's 3 6/10 long. All right, the question is, how do I get the lengths of, and by the way, I'm going to have to come up with another name here. I'm going to call this point O. And I want to know what the length here of AO is. Oh, I don't like the look of that. I want to know what AO is. That's what I'm trying to get. And OB, and ideally, I would like to make sure that they are partitioned in the same ratio, 3 to 2. So how can I do that? Well, we always get lengths on the coordinate plane using the Pythagorean theorem, or we could use the distance formula. The question is, what is the location of point O? We need to know that in order to get some triangle side lengths. So first off, we certainly know that O, from an x dimension perspective, is right above here. So we know that this value here is 6 4/10. So we know O from an x perspective is at 6 4/10. What we don't know is what the y is. It appears to be, if I look over here on the graph, it appears to be a bit over 2, but it doesn't look as high as 2 5/10. So we're looking for that value. And the reason why in the previous chart I had slope is that's the easiest way to find it. Now that's not the only way to find it. We could do a system of equations. We could come up with an equation for a line AB that overlays this segment, and then we can substitute in x equals 5 4/10. We could certainly do that. But the easiest thing to do, I think, is to use that slope formula. So we've got slope equals that delta y over delta x, and we looked at what that formula looks like. And we know that the slope of this segment, AB, is 2/9. So I'm going to substitute that in for and I'm going to put in this value here. It's just a variable y minus, and I'm going over here to point A. I could just as easily use point B, but I'm going to use the 1, it's just a little easier numbers. And then I've got x here of 6 4/10. And I'm going to go over here to the 1 again, 6 4/10 minus 1. Let's simplify that. 2 over 9 equals y minus 1 over 5 4/10. If I cross multiply, I end up with 10 8/10 equals 9y. Make sure you distribute that 9. I'm going to add 9 to both sides. Equals 9y. That's a 9, not a 4. And then I'm going to divide by 9, and I think you can see that that is exactly, not approximately, exactly 2 2/10. So I'm going to go ahead and get rid of this here, and I'm just going to rewrite this now. This is 6 4/10 and 2 2/10. And that certainly does look like it would be about 2 2/10. All right. We're going to move on, and because this is so filled up and messy, I've repeated the same chart up. So I just want to now have a little bit of free space here. This is our 5 4/10, and we've got 3 6/10. And we found that this point O here is at 6 4/10 and 2 2/10. All right, so now we have to find what these values, what these lengths are, AO and OB. And we're going to do that as we always do with the Pythagorean theorem or the distance formula. So I'm going to work on this triangle over here to the left first. And I have one leg length that's 5 4/10. I just need to find this other one. If point O is at, from a y perspective, 2 2/10, and point A is at 1, then this side here is at 1 2/10. So I've got c squared equals a squared plus b squared. I'm going to go ahead and put in AO here. AO squared equals 5 4/10 squared plus 1 2/10 squared. If you go through this math, you will find that the sum of the squares there comes out to be exactly, I guess, 30 6/10. And if you take the square root of both sides, AO is approximately, I'm going to say 5, and I'm going to go out, I think, to the thousands. 532 thousandths. So that's what that length comes out to be. I'm going to label it over here. Now, we have to zoom in. I think I'm going to do this in red. We got to zoom in on this other triangle here. And this value here from a y perspective, okay, right here is 2 2/10, and up here is 3. So the difference between those two is going to be 8/10. And this other value here, we already have it labeled. This length here is the 3 6/10. I might as well put that up here. So again, we've got c squared equals a squared plus b squared. And I'm going to substitute in here my name of my segment, OB squared equals 3 6/10 squared plus 8/10 squared. And if you use your calculator, the sum there is about 13 6/10. And so OB, when you take that square root, is approximately, I would say 3, I'm going to go out to the thousandths again, 3 689 thousandths. And so if we sum these two together, that should be exactly what the square root of 85 is, because that's what we found this entire length to be, is the square root of 85. So we can verify that. That should be the sum of what we found on the second page. And it's also good just to make sure, are these the same ratios? The ratio of 5 4/10 to 3 6/10. Well, that ratio is 3 to 2. We don't even have to do the math on that because that's what we fixed it to be. So this is 3 to 2. I'm going to put that over here. And let's ask ourselves a question. Does that equal the ratio of 5 532 thousandths over 3 689 thousandths? Well, if you actually do this division now, you will end up seeing that this number over here is an approximate number. I really should do approximate. 1.49995, which is really exactly what we're looking for. Now, why is this not exactly 1 5/10? In other words, 3 to 2. Well, it's because these are rational numbers that we're dealing with, so it's not, I mean, we absolutely are going to have very, very slight error in our approximation. Okay, hope this helps. Take care.